Okay, so our plan today is to look at the heat equation, and we spent enough time deriving it, so I'll just locate the appropriate presentation. So we're going to do the heat equation, and it has a lot of interesting techniques and results. So this is heat or diffusion. dT, temperature with respect to time, alpha, del squared temperature. So you have to define what's going on here. This alpha was thermal conductivity divided by density and specific heat. The temperature is a function of position and time. So you're doing a partial derivative with respect to time here. And this del squared, that is the operator, div grad, in Cartesian coordinates, it's the sum of these second derivatives. dy squared plus d squared dz squared. So that's what we want to solve. And what we're going to work on is the one-dimensional version. So solve one-dimensional version of this. And there we have t equals t of x and time. And we're going to rename it. We're going to use, not an implication, but we're going to use u of x and t, temperature and diffusion equation. And then we have partial u with respect to time is equal to alpha e squared u dx squared. And that'll be enough. That'll be enough to interest us. Okay. So first of all, physically, so we have to solve this thing. But it's good to have some idea of what's going on there. And physically, we could say we've got some temperature distribution on the x-axis, and it's going to have some initial value. So say the temperature is distributed like that initially. Okay. So it's essentially it's concentrated around origin. What's going to happen as time goes on? There was energy conservation in the making of this equation. What's going to happen as time goes on? So this is at t equals 0. It's going to diffuse out. So sometime later, you're going to have a distribution that looks like this. And since it's open-ended, x goes from minus infinity to plus infinity, it'll eventually all diffuse away. So the temperature distribution will just get flatter and flatter as time goes on. Does that make sense? And so energy is flowing to the left and to the right. So that's what we think physically will happen. I'll just put here physically. And then here at later times. So now we want to go about solving this thing. And we're going to use a Fourier integral approach. So we're going to say let u of x and t so minus infinity plus infinity, you're going to need a u hat of k and t, because we're used to just doing this with u of x, right? So if we forgot the t, we'd have u hat of k e to the I kx dk. That would be the solution we're looking for. So we have to find what is this u hat of k and t. Okay. Now the differential equation is right here. So if we differentiate with respect to time the partial derivative, I'll just write differentiating. Actually, let's go ahead and write it out. So we'll have the 1 over root 2 pi minus infinity to plus infinity. And we're looking at the left side there, so the explicit time derivative, we have a d u hat of k and t partial with respect to time e to the I kx dk. So what about the right side of the differential equation? 1 over root 2 pi minus infinity to plus infinity. So now we have an alpha. Actually, let's look at what's going to happen. We're going to take two derivatives with respect to x. So it's going to bring ik and then squared. We're going to have an ik squared, which is a minus k squared, and the alpha is going to be multiplied there as well. So we're going to have minus k squared alpha, I'll put parentheses around there, u hat of k and t e to the I kx dk. So we did explicit time, we did alpha d squared u dx squared over here. And you know, we've done this once before. We're identifying the integrand. So apparently, d u hat k and t with respect to time equal to minus alpha k squared u hat of k and t. So this is already a piece of info that we could use. Because when we have the derivative, first derivative, this quantity here, there's an exponential function that's doing that. So actually, I think I can fit that right here. So my u hat of k and t is going to be a u hat of k. I'm going to substitute somewhere in a moment. E to the minus alpha k squared t. Right. Explicit time derivative, that brings down the minus alpha k squared. So in fact, I have an unknown function here of k. I'll just write f of k e to the minus alpha k squared t. So far so good. Question?
I'm a little confused about where we got the k squared alpha from in the first place.
Okay, thanks. Let's go back to that. So we were applying this operation here. So du dt equals alpha d squared u dx squared. So we were applying this operation right up on this. So the left side of this equation is du dt, and if this is u, then the du dt, I just differentiate under the integrand, okay? The right side, again, it's alpha d squared du dx squared. So if I do alpha times this and take two derivatives with respect to x, I bring the ik squared. That makes sense?
Gotcha.
That's a good one. A good one to stop on and make sure we see what's going on there. And then I'm just equating what these two things have, and so I was just equating this here and this here, because everything else is the same. So yeah, that's where that came from. And because it was an explicit time derivative, that's why I can put that up there right away, because that's the exponential function. But that means that this u hat of k and t separated into a function of k and this exponential function of t. So I just renamed that for the moment. Okay. because this is still unknown. This f of k is still unknown. Good, so let me clear a little more board space. So we're just going to take what we have back into u of x and t. So now we have u of x and t is equal to 1 over root 2 pi integral. And then my u hat of k and t, I've got f of k e to the minus alpha k squared t e to the I kx dk. So now there's another condition I can take advantage of. I just erased it, but I had talked about the initial condition. Remember I said there was an initial temperature distribution. It was going to creep out to left and right in both directions. Okay. So, it's all right here, but u of x and t equals 0, but let's write here initial condition. U of x and t equals 0, we get this 1 over 2 pi. So what do we have here? We have f of k e to the I kx dk, because we plug in the t equals 0, just get the 1 there. And what we're looking at here is we now know the identity of this mystery function k. It is the Fourier transform of the initial condition. So f hat of k is the Fourier transform of the initial condition. Initial condition. My notes, I gave it another name, but I think we just leave it f. All right, Fourier transform of initial condition. So of the initial condition, u of x and t equals 0. So that, what we do now, we assume we know that, right? Because we were, well, we can calculate it because the initial condition is given. So the initial condition is given. Is a given of the problem, okay? So we can actually plug everything in now. And I saved some steps for you guys to do as I recall. Let me see. Well, I'm being given initial conditions given as phi of x. So it's f hat of k is equal to phi hat of k. So we could have put this at the beginning of our presentation as well. Just to keep what we have. So now we're just gonna insert one of these objects into the other, and you guys will do a couple calculations to complete the project. Okay, so I'm gonna go ahead and erase this and discuss what we have here. So putting these things in here, and then we're going to have u of x and t over root 2 pi integral. But now we're putting in that Fourier transform the Fourier transform itself is 1 over root 2 pi, again integral, minus infinity plus infinity, b of y e to the minus I k y. I need to use a different integration variable, dy. Okay. So that's the Fourier transform, we'll label it as such. And then after that, we have the e to the minus alpha k squared t e to the I kx dk. So there's a bit going on here. Let me just label these things for you. This was that Fourier transform. And I just used a different integration variable because x is taken. And they're both minus infinity to plus infinity. And what we'll do is just reverse the order of the integration. And then I'll set you guys up with a couple of steps to do on your own. So we're going to reverse the order. We'll multiply the square roots together. We got 1 over 2 pi. We'll do the dy integration, so we'll put it first. We'll put the phi of y here. And then in here we'll have e to the I k x minus y from these two. I k x minus y minus alpha k squared t. Sorry, this one gets an integral sign too. So we did the y integration first. Integral dk. dy, like that. So here's your project. We got a few more steps to get to the complete solution. So the first homework project is to simplify this and evaluate it. I'll put this in 2 steps. Okay. So we're going to take these right here. So e to the minus alpha t k squared plus I k x minus y. We want to factor out an e to the x minus y equals e to the x minus y squared over 4 alpha t. It's got a minus e to the minus alpha t k minus I x minus y to alpha t squared. It's one of those completing the square assignments. So you're going to take this, which is what we're given, and turn it into this right here. And that's what this is going to do. It's going to take this part outside of the dk integral. So having done that, then this entire integral here is going to have this out front, e to the minus y squared or alpha t. And you have this under here, and that integral is going to be wrong star. The star is this one. And that's just going to be root pi over root alpha t. So this is a version of a calculation we've done before. Okay. So you guys will get that. And then this, for the next thing, is to take this result back into here. Okay, and then we'll just write it out, and that will be the actual result, the preliminary result of the calculation. So this gives you a couple things to do. You just have to rearrange this expression into this form, and having done that, this part comes out of the integral, and the rest of the integral is given by this, okay? That'd be a good one to discuss next week too. Okay. So, now we'll write down the solution by just plugging that result in, and then we'll see where we stand, okay? So here's our result. Actually, u of x and t, you'll end up with a 4 pi alpha t root in the denominator, integral minus infinity plus infinity e to the minus x minus y squared for alpha t phi of y. Remember, that's the initial condition, dy. And that's a 4, okay. So good, when the dust settles, we gotta study this for a moment, and then we'll do one more important simplification. So that is the actual result. Okay. Good. So yeah, let's focus on this thing for a moment, because this is, of course, a bit complicated, not that easy to visualize what's going on. We're gonna help that. So first of all, you can just see it's a function of x and t as required. And so we're integrating over y. So the arguments on the right side are this t here in that denominator, t right there. And it's a little confusing for t goes to 0, because here you have something that's diverging, but here you have something, because it's in the denominator, then e to the minus something, this crushes everything in its path, so to speak, right? This thing here, e to the minus something where t goes to 0. So you're getting, we get something finite there, that's no problem. And you're integrating this initial condition over y. Initial distribution. Distribution, you know, v of y equals u of y, t equals 0. Okay, what turns this into something we can actually visualize and understand a lot better is what we're going to do is choose phi of y to be an infinite spike. And this will take us into delta function as well. So this phi of y is a spike. So let phi of y be an infinite energy spike, which I'll define. That's not the technical term we're used to, at the origin. So the idea now is that we have at the origin, you know, we're integrating y from minus infinity to plus infinity. So as far as x goes, it's at the origin too. So the idea is that we have this spike or a point of energy, and at t equals 0, the clock is going to start, and this is what's going to diffuse out to the left and right. Okay. So it's really what I had before when I had kind of a hump-shaped thing, except it's more extreme. What I had before, I said, okay, let's have a distribution like that. And now what we did, we just made it infinitely narrow and infinitely high. And the idea is the integral over this spike would be equal to 1. Something we've kind of encountered in some of our practice problems from back up. So formally, this is phi of y equals some constant. That's a constant times this delta of y, which is the Dirac delta function. Which is our next object of study. But for now, what we have is integral phi of y dy from minus infinity to plus infinity. This is how this thing is equal c delta of y dy equal to c. So the idea is that spike here, this delta of y represents a spike, and its area is 1. It's narrow and high. Okay. Narrow and tall. So the thing is, if you take that as your initial condition, this thing simplifies to something that we can wrap our minds around. I'm going to erase this. So this is the homework part here. And now what we have is u, x, and t is equal to c divided by root 4 pi of e. So that's the c that just came from putting that spike in there, and that spike exists where y is equal to 0. So we're getting rid of the integral, and we're plugging in a 0 where y is, and we picked up that constant c, so now we have e to the minus x squared over 4 alpha t. And that's much easier to look at. Good. And this is the prototypical behavior of a local pulse of energy as it diffuses out. And what's going on at t equals 0 is a little confusing. Okay. So what we do is we just look at it for any finite time. And for any finite time, what does this distribution look like? Okay. For any finite time, this e to the minus x squared is equal to 1. Right, at x equals 0. So you have some kind of e to the minus x squared. It's being multiplied by 1 over root t, okay, times 1 over root t. So because of that, it has some form like that. And for time getting smaller and smaller, you always have this becoming narrower and narrower, and this taller and taller, right? So there's your delta function property in there again. So as t goes to 0, in this expression here, you're getting something that's infinitely narrow and infinitely tall as constructed. As soon as time starts, it's going from this spike down to a lower distribution, and of course eventually, as advertised at the beginning, it's flatter and flatter like that. Peak was supposed to be centered right here. Never mind, I'll confuse the issue more. Okay, you see it in your mind's eye. There's the question. This thing making sense in your mind's eye. You know e to the minus x squared, right? That's a Gaussian. And the smaller t is, you know, the greater this expression, x squared over 4 alpha t, and therefore the steeper the Gaussian is. At x equals 0, it is always 1. So yeah, it's becoming narrower and narrower for t goes to 0 and higher, and then for t gets larger and larger, it vanishes out. Good. Okay. So let's see. That's the discussion of the heat equation. And what we want to do now is start talking about the Dirac delta function a little more. This was an introduction to the idea of the Dirac delta function. I kind of mentioned it when we were doing integral theorems, and we'll pick that topic up again as well. But yeah, the Dirac delta function is this kind of a spike, and it plays a big role in mathematical physics. So I think the first thing I'll do is give another physical idea of the Dirac delta function, or where do these kind of spikes come into play? For this temperature, what we were just thinking of was a very localized amount of energy, very close to localized. You know, this amplitude is just its value, so it's really localized. So let's see, I have a couple of good examples here. That one out of mechanics, I think, is the best one to use here. Let's go ahead and do it this way. So we'll call this delta function. So the idea is we have delta, I'll just use x, delta of x is equal to infinity at x equals 0, and it's equal to 0 at x not equal to 0. So that's not really a function. Okay. But what we do is we say the integral of delta of x dx over the entire axis here is equal to 1. And this is what we did over here with y instead of x. So that's the process we used so far. And you know, on some of our homeworks, we've been talking about this. We were looking for the Fourier transform of a spike once. I'm just going to write here, recall f of x equal to what was that, 2 over a for minus a less than x less than a, and 0 for x greater than a. So we've been looking at these kind of spikes for a while, minus a to a. And the point of these was that, the point of this construction was that the area under it was equal to 1. And we had done some Fourier business with that. So we've seen something like that before, but we hadn't really taken that limit a goes to 0. So in mechanics, we have something similar. Namely, here we have a spike of energy for the temperature impulse. Anybody remember anything about the impulse back in mechanics? This is when you're studying collisions. You can do this. Let's say m dv dt is equal to f. That's Newton's law. And then you can say m dv is equal to f dt, and integrate both sides. And on the left side, you're going to get m delta V, which is a change of momentum, and on the right side, you're going to get integral F of t dt. And no, we could even say minus infinity to plus infinity. That'd be true. So if you integrate the force on something over time, it gives you the change of momentum. Okay. So, change of momentum. And this one is the impulse. So anybody remember studying that? We were talking about collisions, for example. Now we don't generally use the impulse just for any old force. What we tend to think of as a sharp blow. This is a sharp blow, a spike of force, but the result of it is just a change of momentum. So, what would be a good example? If you drop a bowling ball, hopefully not on your foot, but the change of momentum is just going to be the mass of the bowling ball times the velocity it acquires before it hits the ground. Okay? But that's going to be an extremely sharp blow, and if you were to hit a scale with that, it would be a huge force because the time duration is so small. So when you talk about the impulse here, you are looking at something where you have f of t, and then the thing is falling here, and then boom, you have a spike. But the integral over this thing is very short time and this very sharp, large force. The integral over it is simply mass times change of velocity. So this comes into play in physics and mechanics already. So it's not just a formal device at all. But the limiting case is when you make this, infinitely small duration, the force would be infinitely high. The result of it is just the simple m times v. So there's your bowling ball example. Good. So you see how I really waited for the time it took for me to release something for it to hit the ground at t0. So we can generalize this delta function here. We can have so for our delta function, we're going to have, we have an integral f of x delta of x minus x0 dx. So now where is the spike? Using the same definition here, when the argument vanishes, you have your spike. So now the spike is when x is equal to x0. And therefore, this kind of completes the definition here, equals f of x0. That's the whole process with the delta function. It's an object that you can put in the integral. It has that spike quality, and it's such a narrow, high spike that here's what we imagine. Here's our function, f of x. But at x of 0, we multiply it, and it's multiplied by 0 everywhere, except at x of 0, it's multiplied by that very high spike, and therefore, if I do that integral, I'm just integrating 0, 0, 0, boom, f of x0 times something that turns it into 1. So this is what you have procedurally. You have integral f of x delta function picks off the function at x of 0, picks off the function wherever the spike is. Good, so now we can get a little more formal with this. I have a list of possible delta functions. This list is probably as good as any. Let's see which list is better. We'll just take this right here. So first one, so I'm gonna make a list of these. And the way to treat this is to form a sequence of functions whose limit is an actual mathematical spike. So that's our next topic. So functions whose limit turns into a spike of this type. And the example I just had here from previous work is the one we'll start. So the commentary here, the delta function is not a true function. Put it in scare quotes. It's not a function by our ordinary definition. So what we'll do is we'll define a delta sequence. And the delta sequence is a sequence of functions. So we'll have delta n of x, delta n of x, n equals 1, 2, etc. with integral delta n of x dx is always already 1, and then the limit of these, and limit as n goes to infinity of the integral f of x delta n of x dx equals f of 0. So these will all be functions, and we'll easily put up a bunch of these. And that has that same property, and of course I can do the same thing with the x minus x0. Yeah?
Would it be really correct to call it a function operator?
Is it? Yeah, it's an operation. So yeah, you could call it that. Exactly, it's an operation we do on a function. And what we're also gonna see, we often have an operation that we're doing and we locate the delta function in there. And the Fourier method will be an example of that. Good, so this is how we turn the thing into something mathematically legitimate, so to speak, or more legitimate. By having a sequence of these, which are functions, sequence, I'll write here, of functions, delta n of x, etc. And then if you take the limit n goes to infinity, these things become so peaked that they have the formal property. So the first one we'll do is the 1 over n, and then we'll just take it from there. So first example, and actually these make nice problems for calculating. We're going to let delta n of x equal that's right, n over 2 for x less than 1 over n, 0 magnitude of x greater than 1 over n. So that is that spike. That's that spike, and this time, since we want to have them in terms of n, this is the perfect example to start with. So what we're looking at is minus 1 over n plus 1 over n. And the height of that spike there is n over 2. So you see what you have. You have n over 2 times 2 over n is equal to 1. So the area under this is always 1. And as n goes to infinity, this is getting narrow and narrow, taller and taller. So this one does the trick, right? This one satisfies the property over there, and it's going to pick off that value there. And the same, we could have just shifted this x minus x0, the whole thing would be shifted. Now the problem with this one is it's not yet a smooth function. Okay? So the other examples we're gonna do are smooth and differentiable. And I may start putting these on the homework. So where did this week's homework start? With this differential equation. I mean, that's next week's homework, right? The differential equation problems. Do we have enough for this week already? If not, we had something. Okay. We're definitely gonna have more for next week. Good. So the other example, this one's kind of fun. Delta n of x equals n over pi 1 over 1 plus n squared x squared. And so what we're going to do on these examples is prove that they really are a delta function. Prove that they really have this property here. This will look familiar. It will in a moment. Okay. Let's graph it first. So the idea is that with increasing n, it gets taller and taller. Okay. 1 plus n squared x squared. With increasing n, you're ending up with n over n squared for larger n. So it's definitely going, it's definitely going to have this property. Get taller with n and get narrower with n. Okay. But do we recognize this? Should have saved this for the exam, but let's do this. N squared times 1 over n squared plus x squared. I'm giving away the game here, but that's all right. So we have 1 over n pi 1 over x squared plus 1 over n squared. What do you guys think now? Can we do that integral? This is our standard, this is our first example for contour integration. Right? So we'll be able to prove this one. I'm going to put this on homework. Right? Homework, prove delta n of x is delta sequence. Right? Prove this. This and that. So that's interesting because this is something we've done a lot of work with already, and we've been able to modify it into a delta function. This one we've also seen before. So there's a handful of other ones we should look at. And you know, I feel like I'm gonna have you guys do these. Because these are good review, okay? Yeah. So the other example, my number can be as I am. So example 1, example 2. So for 3, we have delta n of x equals n over root pi e to the minus n squared x squared. And again, what does this look like? It's going to grow linearly as n increases, and it's going to become sharper and sharper as n increases as well. It's the Gaussian. Okay. So the homework for all of these so far, you can even include the first one, although that one I can say is trivially done, is to prove that the integral over this is always equal to 1, and then it therefore turns into a delta function as n goes to infinity. recognize that this is something we had from the Fourier transforms. So I'm going to now this one here is a slightly different one. Put this down here. Divergence of vector r divided by r cubed. Now this one I haven't put the normalization in yet, but remember we calculated this last time and we saw with the Gauss's integral theorem that there was a delta function properties. Because this thing was zero everywhere, but it wasn't zero at the origin. So we had this in the previous lecture. So in the previous hour we had this, and what we have is divergence r over r cubed equals 0 for r not equal to 0. It has that delta function property, and it equals question mark for r equals 0. Is it infinity? Who knows what's infinity? But the idea was, if you go integral divergence r over r cubed d volume, and remember we turned that into integral, I'm just going to write here v, Gauss's integral, that was v here, okay? Gauss's integral theorem was r over r cubed, and at the area, and if this was the boundary of a sphere of radius, say capital R, then we had enough powers of here. We had 1 power of R and 2 here to cancel the R cubed there, and we ended up with what? 4 pi, right? So go ahead and review that. Okay. Go ahead and review this using Gauss's integral theorem, using this thing. In fact, you should actually check that calculation out as well. You know, we'll do all that stuff. At least we can tackle that stuff in the recitation as well. And here, when I say equals question mark for a sphere of radius capital R centered on the origin, that's implied there. Because that n hat is itself just r divided by r. Okay. Vector r divided by magnitude. So you have vector r cubed, vector r divided by r, and take it from there. Good. Do we have any more of these? One more thing I wanted to wrap this up with. I got it. Good. Before we hit I'm gonna erase this. Because you've done this before with Gauss's law, you would have, we'll just do an arrow, we'll end up with r squared, r to the 4th, 4 pi r squared, 4 pi. But you want to go over that and make sure you see it. You'll get there. So it turns out that this thing had that same delta function property, and so it shows up a lot in physics because of that. Gauss's integral theorem is used all the time for precisely that. So we have a couple of good examples, you can try all these out, and what I'll end with is the whole Fourier integration. Transform, so the Fourier transform, and let's just write our definition down and see what happens here. So we have f of x, 1 over root 2 pi, so we can do a bit of this, f hat of k, e to the I kx dk. And right under here we have the f hat of k, 1 over root 2 pi. We're going to use a different variable this time. It's enough to do f of x prime e to the minus I k x prime e x prime. So the reason I'm doing this is because I want to plug this integral into the top one. Okay. So I had to choose a different integration variable. So f of x equals, we actually saw this at one point. We're going to take f of x prime 1 over 2 pi integral f hat x prime, here we go. There we got that. This is going to be e to the I k x minus x prime, right? We've got the minus sign on this one, plus on it, so minus k x minus x prime. dk minus infinity to plus infinity, close parentheses, dx prime. So yeah, now let's study this one for a moment. So we've got f of x on the left side. And what has to come out here on the right side? The right side also has to be equal to f of x, because that's what it is on the left side. So what that means is this itself is a delta function. This is delta of x minus x prime. This whole thing is a delta function, and when x equals x prime, boom, x prime equals x. It brings it out. So this, which is very close to what we've been looking at in the past, this itself is a delta function. And what happens in practice, you recognize this thing in the course of the calculation, and life is suddenly much simpler. And you've got something complicated, you extract or you recognize a delta function in your expression, and boom, you've reduced your problem considerably. Okay. So yeah, these play a big role, they're really useful. And those three that I gave as assignments, you'll easily see what's going on. They all represent things that we've done in analogous form, related form. Good, so that's where we'll close it off for today. Let's see what we have left in this. Well, we'll start with this next time. There's a little bit more to do. And that gives us enough to talk about next Monday and Tuesday as well. You guys get a